but it's very dangerous. It's like Martina Navratilova falling over the cliff. Remember this morning? Okay, the lecture this afternoon is about emergent structure, and take a look at your handout here, page 30, and in particular, let's look together at the nature of the problem. The problem is described on the first page of the handout. That's page 30 in the book, page 1 in the handout section. Now, we've been talking about linguistic structure on the one hand and construction of meaning on the other hand. And we saw that this morning and yesterday we noticed two aspects that are important, that are crucial for meaning construction. On the one hand, compared to what the linguistic structure actually tells you, the meaning you construct is, in fact, much richer. So that means that in any particular context where you have a linguistic structure that is motivating you, that is prompting you to construct meaning, you are doing creative work. Even though, again, it's unconscious, you don't notice it, other people take it for granted, they find it easy and automatic because all humans do it. But in fact, there is a lot of creativity involved in using language at any given moment because, of course, the language you use needs to be adapted to a particular context in the ways that we saw this morning. So you end up calling up all kinds of structures, frames, ICMs, and so on, that are different for every context that could be paired with the same linguistic structure. A single linguistic structure can produce many, many meanings, but it's not the linguistic structure that produces the meanings. It's you in your mind, by using the linguistic structure in a particular context in order to build the corresponding network. So the last example that we saw this morning, for instance, the very complex example of should I kill my daughter in order to, be better or something, or to walk, you could see that in that particular context, in order to understand the expression, we had to build a very elaborate network of connected and blended mental spaces. The same sentence in a different context would have, of course, a completely different set of networks associated with it. Therefore, in interpreting or in building meaning ourselves, we are always creating new things. Now, in addition to that, there is the issue of creativity in general. That is, when humans produce things that are novel, that had not been produced before, and that can then be used by other humans and transmitted to later generations. And I will show you this afternoon that certainly a great part of that creativity is also possible because we have the mapping and blending schemes that we have. So there's creativity in the short term, right on the spur of the moment when you're interacting with other people, speaking, talking, thinking. And then there's creativity in the long term where a particular group or a particular culture elaborates very special blends that can be used later and that can be transmitted. Okay? So those two aspects of creativity are important. So if you look at page 1, that is page 30 in the book, you'll see 5 aspects of the problem of emergent structure that are pointed out. Emergent structure in blended spaces is more than the projection of new relations. It is literally the creation of new things in conceptual worlds. So that's problem number one. How is this possible? How does that happen? Problem number two, the power of the emergent structure is not just in the blended space. If you have a blended space by itself, that is often a very simple structure, like the man snatching food from the children. But the creative emergent structure that you get for the entire integration network is precisely the result of linking the blended space with the other spaces, with the other inputs in the network. Then, number three, at the same time, blended spaces often have extraordinary properties. We saw that in some of the blended spaces that we used as examples. Children become accomplished surgeons. Numbers can suddenly be rotated in space, and so on. And so, again, the blended spaces by themselves are easy, it turns out, but how do they fit into the creative nature of integration, thinking, talking, short-term, long-term? Number four, the new things that we create in such surprising ways are generally conceptualized as having always existed. I will show you this for numbers. That is, instead of considering them as new inventions, after inventing them collectively, we then conceptualize them as something that was already in existence, independent of ourselves, and that we sort of discovered. Okay, I will get to that later in the same lecture. And finally, integration networks allow the proliferations of non-things in our conceptual worlds. And we saw that with the missing chair, and we saw that with the missing daughter this morning, the daughter Zara, and we saw that with the number 0. So it's an important component of emergent structure and creativity to be able to manipulate non-things, things that really are not things, because they point to absence. Okay, so those are the 5 mysteries, if you like, that we will, this afternoon, we'll take a look at some of these mysteries and see how far we can get. So, page number 2 on the handout, there's a reminder here. The first example of conceptual blending that we studied was called regatta, and that means the sailboat race. What was emergent structure in that example, in that piece of data, the sailboat race? Well, remember, the inputs, the factual inputs, what was actually either happening at the time of the magazine article with the catamaran, trying to go fast, or what had happened before with the Clipper, Northern Light, the old ship, in the previous century. Those were factual events that happened at different times and that were remembered by the people either observing them or remembering them. But in the blended space, we had something imaginative that was not really happening, and that was a race between the catamaran on the one hand and the old ship, the Clipper, on the other hand, even described as a ghost. Okay? So what was emergent in that blended space was the notion of a race. Now, the race itself was taken from familiar frames. We know about races. We didn't have to invent racing, of course, to get that particular emergent structure. But what was emergent was the idea that those two boats, who actually existed many, many dozens of years apart, those two boats were actually racing together, competing, that the captain of one was watching the other boat and making sure that he was ahead and feeling emotions. So very often, as a result of building blended spaces, we have emergent logical structure, but we also have emergent emotional structure. Why? Because the emotions are tied to the new frame that is in the blended space. In the case of the boats racing, we have emotions now that we have in a race, competition, trying to win, trying to stay in front, and so on. in the example this morning of, remember, the politician vetoing the bill that would have, given foreign aid to poor countries and allowed feeding children and so on. In the blended space, we had this bad, nasty politician snatching food from the children. That was, on the one hand, what we called a human scale, a much more directly apprehendable scenario for us. We can see the bad person taking food. But these human scale scenarios are typically associated for humans with basic emotions, with fundamental emotions. When we see somebody snatching food from the child, we're angry. When we just hear a report in the newspaper of a bill being signed, of transportation of goods, of all that, it's not something that triggers emotions. So one of the functions of blending is actually to reinforce the emotional reaction to some events or some news or some reports that are going on. Well, that emotion is also, of course, part of the emergent structure that is created. The emotion was not present by itself in the input of the man snatching food from the child. It's present if somebody is there watching it, but we have it only as a frame. And in the other input, the politician, the politics, the voting, many intrigues, and so on, again, we don't have strong emotions. But when we build the blended space and the person is actually seen snatching the food, then there is an emergent emotion. So, in the case of the boats, or in the case of the snatched food, or in the case of the man riding with Hitler, all these cases that we saw, the emotions are emergent in the blended space. We have both logical and emergent structure. With a man riding with Hitler, you say, what? How can that guy, be giving a ride to Hitler? He's a traitor, okay? Whereas in the more diffuse input, where he's just using a little too much gas, you don't feel the same emotion. But with the blend, you manage to make his relatively insignificant action of using a little too much gas, not sharing his car, you manage to make it into a treacherous act where he is giving the enemy, Hitler, a ride in his car. So you can see all this is creative emergent structure that is happening. And again, you can see that one of the ways that this happens is because instead of just combining the inputs, we are bringing in other frames. We are using pattern completion to end up with a richer blended space. So to look in some more detail at the notion of emergent structure, I will return to an example that's in your handout, and that's also in the book, in chapter 3 of the book, The Way We Think. And it's the example of the riddle of the Buddhist monk. And this riddle was actually cited by Arthur Koestler. Arthur Koestler is a famous American writer who's written about many things. But one of his books is called The Art of Creation. It's a very interesting book. And one thing that Arthur Koestler noticed is precisely that many acts of creation consist in bringing together things that seem incompatible. You bring them together, and somehow out of the incompatible emerges something new and interesting. Now, Koestler didn't know how this happened. He just noticed that. Very interesting observation. But now, with blending theory, conceptual integration, we can actually give a more scientific, precise account of how this is possible. And in particular, of how double scope blending is the key to a lot of human creativity. So here's the example from Koestler, the riddle of the Buddhist monk, and it's just a puzzle. You're asked the following question. You're told that a Buddhist monk begins walking at dawn and goes up to the top of the mountain, and he stays at the top, and then maybe 2 weeks later, he goes down the mountain again, he starts at sunset, and he gets there. He starts at dawn, sunrise, and he gets there at sunset. And the question in the riddle is, given the journey going up and the journey going down, is there a point on the path where the Buddhist monk is at the same time, like maybe 3 o'clock in the afternoon, on the way up and on the way down? And this is not a hard puzzle mathematically. You can write 2 little equations and you can find the answer. But there's also a more direct way of finding the answer, which is this. Instead of imagining the 2 separate journeys, you blend them into a single journey. You bring the monk going up and the monk going down into a single blended space. And then one of them is going up the mountain and the other one is going down the mountain. And then you have the insight immediately that, of course, these 2 monks are going to meet. There has to be a meeting point. And that meeting point, of course, if you project it back to the separate journeys, that meeting point is necessarily the point where the monk is at the same time going up, going down. Because let's say it's 3 o'clock p.m., that's the monk going up, meets the monk going down at 3 p.m. So they're in the same position, okay, going up and going down. So the way this looks in terms of blending is you have 2 input spaces, one going up, and this is schematically, this is the monk here going up, and over here you have the monk going down, right? And that's what's happening in the 2 inputs. It's easy to match the 2 inputs. There's a monk, there's a mountain, there's a day, there's sunrise, there's sunset. So it's easy to find the correspondence between the 2. And the generic space, what is common to these 2 inputs, is the idea of a journey on the mountain path, either up or down or any direction. That's what's common. But now the blended space is obtained by projecting this input. So here's monk position A1 being projected here to position A'1, and the monk going down over here, A2, is projected to the monk going down A'2. So in the blended space, you can see the 2 monks going towards each other. Now, this is when pattern completion operates, because now you have 2 people walking towards each other. This is a schema that is very familiar in your mind, okay? Because you're a human being. It's actually a complex schema, but it's one that is very familiar to you. You've often seen people walk towards each other. You've often yourself walked towards other people. So it's not hard at all. In fact, it's automatic to use pattern completion here and say, hey, that's the encounter schema. This is 2 monks coming towards each other. Now, once you have the pattern completion, you can then use the blended space dynamic structure in order to run the blend, to see what is happening in the blend. And of course, what happens in the blend is the 2 monks walk towards each other and will end up meeting each other. So, running the blend will produce the meeting point. And the meeting point, of course, projects back to the 2 inputs and gives you the solution. It's necessarily the same point in the 2 inputs. So the answer to the riddle is yes. The answer is positive. The answer is, indeed, there is such a point. There is a point where the monk will be at the same time going up, going down. Now, the virtue of this example is to illustrate blending on the one hand, but also emergent structure. Notice that we can say, in English, we can use the reflexive pronoun here. We can say, the place we're looking for is the place where the monk meets himself. we can use himself. Now, in fact, in the blended space, it looks like there are two monks. But we also know that in these input mental spaces, we know there is identity between this monk and that monk. It's the same one. So, in the blended space, it's the same monk going up, going down. Now, that looks like an impossible situation, but again, it poses no problem here. And it has a linguistic reflection, namely that we can use the reflexive pronoun. We can say the monk meets himself at point A'1, A'2. Okay. So what we see here is again, a pretty straightforward case of novel emergent structure being built. And with linguistic consequences, because now the linguistic form, the grammatical form, the monk meets himself, is perfectly appropriate to describe that blended space. In other circumstances, you might be told, hey, that's an ungrammatical sentence. It's impossible to meet yourself. You can't meet yourself. You can't be in two places at the same time, so this must be an ungrammatical sentence. But in fact, it's a perfectly good sentence, and it describes the emergent structure of the, again, of this puzzle. Okay, now look at your handout, and let's talk about a couple of non-linguistic examples. It's very important. Remember what I said at the beginning, in the very first lecture. I said in cognitive linguistics, the goal, of course, is to connect operations that construct meaning for language or by means of language and relate them to cognitive operations that we find elsewhere in other human activities. So here is one example, the one on page 4 in the handout, which happened to me. This is a personal experience. I was learning to ski in Utah in the United States. And there was a ski instructor trying to teach me to ski. And I was not very good, so he was trying to, help me. And one mistake I was making was this. When you're a novice, when you learn to ski, you tend to keep the same kind of positions as when you walk. Now, when you walk in the same direction as your feet. Okay? That's pretty straightforward. Typically, you don't walk like this, okay? Very few people walk like this. Or you don't walk backwards except in special circumstances. But in skiing, it's different. In skiing, you're going down the slope, and you want to keep your head looking in the direction of the slope. But the skis, you don't want to go down directly with the skis, otherwise you'll just, go too fast. So the skis must be going sideways, and your body must be like this. So, ski like that, and then you turn the skis, but your body stays in the same position. Now that's hard to do because, again, our instinct is to do, as a novice, I would do this in the direction of the skis, and then I would turn and I would do that, right? So the ski instructor was trying to make me invent the right movement. He noticed I was French. He said, oh, you're French, so here's what you need to do. I had my ski poles, for skiing like this. He said, pretend that you're a waiter in a Parisian cafe, in a cafe in Paris. You know the waiters who bring champagne and croissant and everything? So the ski instructor said, take your ski poles and pretend that this is a tray. And on the tray, you have the champagne, and you have the croissants, and you have other good things, okay? Now, start going down the slope, okay, with holding the tray. Well, now, I was forced to have the right position, because if I made the mistake, you can see the champagne would fall this way. And if I made the mistake like that, the champagne would fall the other way. So the only way to hold the champagne on the tray was to keep my body in the right direction and my feet like this. Okay? So it was a very good coaching instruction from the instructor. But it was using a very clever blend. He was blending the situation on the ski slope, the person learning to ski, with the waiter in the Parisian cafe. So I had a counterpart in the mental space, imagined mental space, with the waiter in the cafe. And my poles had a counterpart that were the tray of the waiter, and so on. And what I was doing was constructing a blended space in which I was a skier going down the slope, but also carrying champagne on a tray. Okay? And of course, this was through imagination because I didn't have a real tray or a real bottle. Okay? So here's a case where by using a clever blend, the instructor made the right emergent structure happen. Okay? And this, again, confirms how embodied these mental constructions are. They can create emergent structure in our bodies, in the way that we move, in the way that we deal, that we interact with the rest of the world. Another nice example, non-linguistic but related to language, is an example from technology, and it's actually an example from computer technology. It's the invention of the desktop. Now, before there were computers like this with, windows and files and folders that you can just transport on your screen, we had to type everything. We had the Unix system, and we had to type all kinds of very abstract instructions in order to move files and to print files and so on. The invention in the middle, the invention was before, but the commercial production of Macintosh computers with this Windows system was in the middle 80s, and suddenly, of course, we had a completely different interaction with the computer. Now, this is the interaction that has, these windows and things on the screen. Now, this is, again, if you think about it, and you can read more about it, this is a very elaborate blend because it takes as one input, it takes the familiar world of grasping objects, moving objects, putting containers, putting one object inside another. Okay, this is things that we do in the three-dimensional, ordinary, everyday world. And the other input is the abstract world of computers, okay, where things are going on in the computer that, of course, you and I don't even understand. And you blend the computer commands with the ordinary actions in order to create this desktop where you do things like you say, move this file or this folder, whatever it is. And you're not really moving anything, of course. You're clicking, and then you're holding the click, and then you're doing something that is a movement with your mouse. On the screen, there are just different pixels that appear. There's not really an object here. There's just something that lights up that you can link to the input of moving objects. And in the same way, clicking, which is just clicking the mouse, will have the effect, of course, of doing something on the screen, and we interpret that as grasping the object. So with clicking, it's like taking the object. And then this is a typical motion of the object. Now, we don't even notice it on the screen. I have colleagues who were computer experts, and they just thought of moving the file on the screen. They had not noticed that on most computer windows, you can check on yours, the way when we move something, first there is a kind of phantom of the thing that moves. The original thing stays in the same place. We click on this, and then we move, and this is the phantom that moves, okay, the dotted line rectangle. And then when we unclick, suddenly this one disappears, and it appears in this position instead. Okay? So it's nothing like really moving objects in real life. When you move something in real life, if I move this bottle, for example, I don't have the bottle staying on the table, a phantom of the bottle, you know, and then when I stop, oop, boom, the bottle appears in my hand. In other words, the structure on the screen is really quite different from the input structure of moving objects. And it's also, of course, very different from the Unix structure of typing in instructions to the computer. So it's an emergent structure of its own, a very interesting emergent structure, which, notice, is very complex technologically to invent. Okay? Engineers who invented that were geniuses. But once you have it, it's a very simple structure to learn. In fact, that's why it's so useful. And you can teach it to children very fast. And children, you know, can learn it, and then they can transmit it to their own children when they grow up. So this is typical of what humans do. They will invent, they will come up with what is actually a technologically difficult emergent structure. But then, once they have it, it will be easy to transmit. In lecture number 8, I will talk a lot more about this. I'll talk about work done by anthropologists and cognitive scientists that, again, show the connection between building meaning in language and building meaning in other aspects of creative technology, creative invention, and so forth. So for the time being, I will just leave it at the desktop case. Again, reminding you that when you use the desktop, here's another case of this object over here is going into that one. So this is a file, and it's going into that folder on your computer desktop. Again, it's the invisible phantom that goes in. But it doesn't really go in because there is no real container there. It just superposes as an image over the image of the other, and that counts as being in. That's what we count as being in. And then once it is completely covered by this shape, then it disappears over here when you unclick. Another property, another funny property of the computer objects is that when you open them, like you open this one, this is a folder, you double click on the folder, you open it up, and what you see is suddenly a much bigger object with files and everything, quote, inside. So another property here is that when you open objects on the computer, they become big. This is, again, not a typical property of ordinary human object. We have no trouble building this new emergent structure. And that, again, is an important lesson. It's like the metaphor example of digging graves that I showed you. We have no trouble building a blended space where you dig the grave and that triggers the death of the person digging the grave, even though it's not at all the usual scenario that we have in the case of funerals and dying and so on. So that's the problem. For the mistake, if you like, of metaphor theory was to think that you always transfer structure from the source to the target. But in fact, all these examples show you don't transfer structure from the source to the target. You actually create new emergent structure in a blended space. And very often that new emergent structure is very different from the structure that you had in the source. In this case, for example, this is a structure of, you know, a container-like structure, movement-like structure that is completely different from the source domain of objects that we manipulate in everyday life. At the same time, it is structured by the frame of ordinary objects, and that's what makes it very easy for us to learn this new computer structure. Okay, on to more abstract examples. I'm going to go on to examples from mathematics. Now, you don't have to know any mathematics to understand this example, even though it happens to be a case where very, very brilliant mathematicians could not find the answer. Okay? So I'm going to show you the blend that actually was the answer to a very important mathematical question. And we're going to discuss a little bit together why the top mathematicians, Leibniz and Descartes and Euler and Bombelli and Cardan and all these mathematicians who knew they needed the notion and they could not come up with it. But once we have it, it seems like a very simple notion. And this is going to be, you might say, well, what does mathematics have to do with linguistics? And of course, my answer, as on the first day, as on Friday, is going to be mathematics, like technology or poetry, has everything to do with linguistics, because the very same cognitive operations are at work in creating, for example, new concepts of number, in enabling humans to understand mathematical complexity or to understand meaning complexity in general. Now, this is not just my strange idea. This is, of course, a fundamental discovery of cognitive linguistics generally. And the book by George Lakoff and Rafael Nunez, the book is called Where Does Mathematics Come From?, is, again, a brilliant illustration of how you can build mathematics with successive blends, blend after blend after blend, which are exactly of the same nature as the blends you need for language and grammar. In fact, they are the same because mathematics is just one area of meaning. Of course, it's not the area of meaning that most of us manipulate, all the time. And that's why, for some of us, it's going to be a sort of unusual area or an exotic area that we don't understand. But it is structured, in fact, ultimately in ways that are very, very relevant to language. So let's look at the mathematical example. And I need to give you a kind of very short version of what the mathematical problem was. The mathematical problem was this. It appeared in the 16th century. It turned out that to write the solution of certain equations, the equations of the so-called cubic equation, the x to the cube plus px plus q equals 0, it turned out that in order to write a very general answer to these solutions, the only way, and the best way, therefore, because it was the only way, a very elegant way, was to use square roots of negative numbers, things like square root of -5 or square root of -1. And this was a big problem because negative numbers do not have square roots. There is no number that multiplied by itself will give you -1 or -5. Because if you take any two numbers, if you take any number and you multiply it by itself, either the number is positive, 2 times 2 is 4, or the number is negative, -2 times -2 equal 4, also, plus 4. So any number multiplied by itself gives you a positive number. And yet, here was this paradox that in the mathematical system, somehow you had to imagine the existence of something impossible. So the mathematicians decided that they would use this in their formalism, that they would use this in writing the equations because it was convenient. And then the funny square roots would cancel each other out at the end. But they also decided that this was an impossible concept. So they said, these are not real numbers. This is just a notation. They are, Leibniz called them impossible numbers, and others called them imaginary numbers, because there was no way that they could exist in mathematics. And yet, you had this very strange situation that these numbers were, in fact, very useful. So they were impossible, but useful. And believe it or not, it took almost 3 centuries to find the right conceptual system where these numbers could fit in, because in fact these are useful as numbers. When the right conceptual system was found, the name of the numbers was changed. Instead of calling them imaginary, they were now called complex numbers. Now, the solution was, when you look at it after the fact, was actually a pretty simple one. It was a blend. You took numbers in the old-fashioned way, numbers like -1, -2, and also fractions, -2/3, and so on a line, okay? You took that as an input, and then as another input, you took 2-dimensional space. So a space with points on it, you know, like this screen. This screen is a 2-dimensional space, and it has points on it. And then you do a mapping of the numbers here onto the line of the 2-dimensional space. And then you project over here into a blended space. Now, in the blended space, you have the line, but you also have all these other points. And these points are now also numbers. So the emergent structure that you get is that you don't just have numbers on a line, but you also have numbers all over the place. And each number now has, here's a number. So this point, here's where it gets very tricky. So this is a number. And here are the old numbers, okay? Numbers like 1, 2, 3, 1/3, 0, and so on. And then other numbers are over here in space. And every number now has a distance from the origin. That's called the magnitude. And it also has a rotation, an angle from the horizontal. So every number now has both a magnitude and an angle. Now, the numbers on this line have either 0 angle or they have 180 angle, pi. Okay. And what happens in this new space is that you have a completely emergent notion of multiplication. And it's a very simple notion. To multiply 2 numbers, here are 2 numbers. Here's a number that has 60-degree angle and 3 magnitude. And this number has 30-degree angle and 2 magnitude. You want to multiply them? What you do is you add the angles, 60 plus 30, and that gives you 90. And you multiply the 2 magnitudes. 2 times 3 equals 6. So here is the number that you get as a result. Now, it's easy to see that, for example, -1 in this blended space, -1 does have a square root, because if you take -1 on the, well, I should have made the schema, but if you take -1 here, and if you look for the number multiplied by itself that will give you -1, all you need is to take the number that's right here, perpendicular, 90 degrees, and has magnitude 1, and then you multiply by itself. 90 plus 90 is 180. You find this position. 1 times 1 is 1. You find -1. So in this new system of numbers, where numbers are points in space instead of being just on a line, now you have square roots for every possible number. The complex numbers, the negative numbers, the positive numbers, everything has a square root. In other words, what we have here is a very different notion of number than the previous one. So this is a case of a concept evolving. The concept of number has changed. It's not different from the way concepts change in other areas of language and thought. Okay? We change our concepts all the time. A concept can evolve. You can have one example we cite in the book And there are just many, many examples. You can go, in American society, you can go from marriage, one conception of marriage to another conception of marriage that includes same-sex marriage, for example. And then you get a number of key features that will change. Or if you take, again, Lakoff's work on, radial categories and cluster concepts, things like mother and so on, you find changes in the meaning of words like mother depending on how you blend them with something else. Mother as the necessity is the mother of invention, or mother as in this person took care of me, she was a mother to me. Okay, so this is a very general phenomenon. But the mathematical case is excellent to illustrate it precisely, because what we see in the mathematical case is that the solution is simple. The emergent system is a simple one. You can teach it to a 5-year-old child. All you need is the notion of rotation for numbers and the notion that you can stretch the number. So if you want to tell the child, number 2, and if you want to tell the child number 2 with angle 60 degrees, you show him number 1, you stretch to 2, and you do 60 degrees. And you've got, right here, at the end, you've got your new number. Okay? And so the child can learn that. And then you say, multiply the thing I showed you, 2 30 degree and 3 60 degrees. First do the rotation for 2, 30 degrees, then multiply by 3 by stretching, and then do the rotation 90 degrees, and there you are. You found your number 6 perpendicular. So the child can learn the blended space easily. And yet, these great mathematicians, Euler, Descartes, and so on, they were not able to find that. Mathematics is interesting. Don't fall asleep. Okay. So anyway, on to, after lunch is not easy. At least I'm running around on the stage, but you poor people, you have to sit, and maybe you have some really good food. Okay, you have on your handout, you have the explanation here of how the emergent structure is created in this interesting case of mathematics. And again, the fact that what you end up with in the blended space is a simple structure. But interestingly, the reason it's a useful simple structure is because it is now connected to the other notions of number, the notions of number that you had before. On your handout now, moving along, on page 37, page 8 of the emergent structure handout, you will find the example of time. And the example of time is going to be very important for us when we study metaphor tomorrow morning. The construction of time in language, as you'll see, is a very elaborate and complex construction. And it has many blends that contribute to build the notion of time. In order for these blends to operate, you need to have an emergent structure that actually comes from human experience. And this is a little bit like the dinosaurs again. So here's roughly how it works. The initial notions of time are presumably built for human beings on successive days. The fact that we can see that there's a day, sunrise, sunset, we sleep, and then the next day, the same thing happens. The sun comes up and the sun goes down. And that gets repeated over and over and over again. So you have analogy connecting these different days. Now, analogy can be systematically, in many, many blends, we find analogy compressed into identity, so that, and in fact into uniqueness. So in this case, the analogous days get compressed into a single cyclic day. And it's like the tax bill. Remember the tax bill example? My tax bill gets longer every year. In fact, you have many different tax bills, and you compress them into a single tax bill that changes size. For the days, we do the same thing. We talk about a single day coming back and starting all over again. So we say things like the day, as if there were a single day. The day runs its course. We go through the day, and then the day starts again. The day starts again tomorrow. Okay. So the day is now compressed to something cyclic. And that is an emergent mental structure, because there is nothing in the world out there that shows you a single cyclic day. Okay? That's a human conception that is created by compressing the analogy of all the successive days into one single cyclic day. Now, later, as people make more and more observations about the day, about the events, about the things they do, of course, over and over again, they need what we now call today a system for tracking time, timepieces, watches, and so on. I went to this, again, I went to the Forbidden City, and they have this wonderful Hall of Clocks. How many of you have been to the Hall of Clocks? Raise your hands. Oh, not many. If you're visiting Beijing, well, of course, don't skip my lecture, but go and visit the Hall of Clocks in the Forbidden City, and they show you all kinds of wonderful clocks from all over the world. And in particular, there are, you know, these water clocks, clepsydras, and other kinds. Well, the invention of timepieces, starting with the sundial, is again a wonderful human invention. The idea, if we look at the modern watch or clock, there's a clock way back at the back of the room there, and the idea of the clock is also simple. It's take the one that has, not the digital, take the one that has rotating hands, for example, okay? So that's going to be one input. It's a mechanism. It's a mechanism that has rotating hands that go around and around. Now, the genius, of course, of clockmaking and engineers who devise clocks is they are able to make clocks that will be synchronized so that they will move at exactly the same rate. The hand on my watch will move at the same rate as the hand on your watch. Now, this is an engineering feat, of course. Once you have this kind of mechanism, you can now take that as one input for a blend. And the other input, you can take the cyclic day that I talked about, the day that starts over and over again, okay? And you can map the parts of the cyclic day, noon, sunrise, and so on, you can map onto the mechanism in various ways, okay? In the history of the world, there have been many different mappings. There are clocks that had hours that differ in length, and hours that are different in the summer and the winter, and on and on. But here's my main point. The main point is the day that you observe in nature does not contain units of measurement. It does not contain seconds and minutes and hours and things like that. The way that we get the units of measurement is by mapping the day itself onto these mechanisms that are synchronized, and then you project into a blended space. And in the blended space, you can now have emergent new notions of time, because you can now, of course, on your dial of the clock or the watch, you can now put little marks exactly at the same distance from each other. And you can have the big hand and the small hand that move at different rates. And that will automatically produce a number of positions here on the watch. And those positions are purely mechanical in the input. But in the emergent structure of the timepiece, those positions now become parts of time itself. Okay? And, okay. Now, this is magic, in fact, because by doing this kind of blending, and of course by doing the engineering of building watches or sundials or clepsydras or whatever, people are then able to create new units of time that did not exist, hours, seconds, and so on. But notice that when this is done, and I'll go back a little bit, just again, I think I put this on your handout, but the important aspect is that you divide your dial into a number of intervals. And if the number of intervals here is 2, and the other number here is 1, we have the division of the day from midnight to noon and noon to midnight. But on the watches that we use, the number n is usually 2. That is, it takes 2 rotations of the watch to get a complete day. And the big hand is 12. There are 12 intervals on the clock. And then, of course, there are sub-intervals for seconds and so on, so that you end up with, n equals 1440 and k equals 60, and you end up with the 86,440 seconds in the day. This is all created by human conceptual blending and, of course, human engineering. Once you've got it, you've got these units of time. And this brings me back to the point number 4 on page 30 of the handout. The new things that we create are generally conceptualized as having always existed. So we talk about time, eternal time, as if there had always been seconds and minutes and hours and everything, as if time was made up of these things. But in fact, of course, time is created by human ingenuity. Okay, let's see. The next part that I want to show you, there's one more thing about numbers. I showed you how the complex numbers were created, and we could say, we could show, I won't do it today because it's after lunch and too much mathematics will kill us, but the evolution of the notion of number is systematically more and more blending. So you start with notions like points on a line, and then numbers, 1, 2, 3, 4, 5, rhythmically counted, and containers, things that have baskets that have 1 egg, 2 eggs, 3 eggs, and so on. And you can map those, of course, onto each other, and then you get the number line with 0. 0 is emergent in there because there is no, when you count, you don't start with 0. You count your friends, you say 1, 2, 3. You don't say 0, 1, 2, 3. But 0 gets added again, emergent in the new notion of number line. And the same thing happens in order to get rational numbers. You have to add fractions, but you don't just add fractions. You actually create a completely new notion of number. You use proportions, things like something is, in the proportion of 3 to 4, and you make that into a number also, so that now you have numbers all over the line. Before you just had 1, 2, 3. Now you've got the line is covered with numbers. Then you go from well, let's see. Then, okay, now you have your fractions and rational numbers, and the same thing happens for the irrational numbers. And the story here is actually an interesting, funny story. It's due to Pythagoras. You know who Pythagoras is? Pythagoras, a Greek mathematician. Pythagoras. Okay? And you probably know the theorem of Pythagoras, right? The square of the hypotenuse is the sum of the squares of the two sides of the triangle. You learn that in school. Well, Pythagoras had a group of mathematicians, and it was also kind of a religious group at the same time, because they had an interesting belief that the universe was governed by numbers and by proportions of numbers. And therefore, everything in the universe had to be a number or a fraction. And then, one of the group of Pythagoras showed very simply that because of the Pythagoras theorem, there were segments that could not have a rational length, that could not be measured by means of a fraction. Square root of 2. So if you have a triangle that has 1 and 1, the hypotenuse is an irrational number, square root of 2. But in those days, there was no such thing as a rational number. All the numbers were the fractions. And so when they found that out, that some segments did not have a measure, this was considered blasphemy. And they were all in a boat together when one of them discovered this. And the others were furious, and they threw him out of the boat. Okay? They threw him out of the boat because discovering a segment that had no measure was blasphemy. Well, of course, what happened later was that the rational numbers were blended with segments of geometry, and they gave you a new notion of number that contained things like square root of 2 and so on, irrational numbers. And this goes on and on and on in the history of mathematics, so that then you get transcendental numbers, and then you get the real numbers, and then you get the complex numbers that I talked about before. Now, again, why is this interesting from a linguistic point of view? Because at every stage, the interpretation is, oh, there were numbers out there that we had not seen, and now we've discovered them. But that's not what's happening. What's happening is people are using blending to invent a new, more interesting mathematical system. And when you reach the end, of course, and that's not the end, you can go further, but when you reach these stages, you suddenly have a richer system. And people think that, oh, we've just added more numbers. But in fact, the whole concept of number has been completely modified using blending. So this is not a special case for mathematics. This is what happens all over. But in the case of mathematics, we can really see it extremely clearly. Let me see if I have a few more examples of anything. Well, that's about it, actually, for this afternoon. So I'll probably stop here. I did want to, maybe it's on the handout, I did want to point out, or to re-emphasize, actually, this is on page 36, okay, page 7 of the handout. There's one line here that is really a reminder. It says emergent structure and causal compressions, because all the causal compressions that we saw this morning, the one with the fruit snatcher, the one with Hitler, and finally the one with Toblerone that I did not have time to discuss, but that you can look at, all those, of course, had rich emergent structure. And I pointed it out this morning and reminded you this afternoon. So the final word for today, the final word about emergent structure is that it appears in many, many different areas. It appears in mathematics. It appears, of course, in creative poetry. It appears in everyday language. It appears in jokes, in humor. It appears in advertising, the case of the children doing the bypass, the case of Hitler and writing alone. And it appears in rhetoric when you argue and when you, for example, you call the politician a food snatcher. Okay? Again, you're using emergent structure that you're creating in the blend. So it's a very key human capacity, and it's one, of course, that language is using all the time, all the time, all the time. Okay. So I'll stop, and maybe we can have a few questions. Thank you.